Looking at the fundamental bits of light and matter, that's the photon and the electron.
That's right. And we're working from some really interesting source material you've shared, which describes them as being locked in this kind of perpetual, intricate dance. It's not just particles floating around. It's fundamental to reality itself.
Exactly. We've got this great collection of insights here describing these two really crucial players.
Yeah, and our goal today, is to pull out the key takeaways from these sources. We want to really get a handle on how they relate, how they interact sometimes in pretty weird ways, and even how they can literally turn into each other.
So think of this as like a shortcut to getting up to speed on something truly basic about how the universe works.
Definitely. So where do we start?
Yeah.
First glance, photons and electrons, they seem like polar opposites, don't they?
They really do. The sources hammer this home right away. Like mass, for example. Photons. Massless. Zero rest mass. Period.
With the electron, it has mass. It's incredibly small. Sure, 9.11 times 10 to the minus 31 kilograms. But it's there. It's got substance.
Right. And then charged photons are neutral. No electric charge at all.
Whereas electrons have that fundamental negative charge, minus 1.6 times 10 to the minus 19 coulombs.
Yeah.
And that difference is, well, it's huge for how they behave in electric or magnetic fields.
Speed's another obvious one. A photon in a vacuum has to travel at the speed of light, c. It doesn't know any other speed.
But a little electron, it can go fast, incredibly fast sometimes, but it's always, always slower than c. It can never actually reach it.
And their jobs seem totally different, too, based on the sources. The photon's described as, like, the messenger particle for the electromagnetic force.
Yeah, the force carrier. It is light, radio waves, all that. Well, the electron is, a chunk of matter, a lepton, one of the basic building blocks.
So just looking at that list, mass, charge, speed, role, you'd put them in completely separate boxes, right? One's energy, one's matter.
Exactly. And that's where the story takes a turn, according to the sources. Because underneath those differences, there's this really deep connection, this shared property, wave-particle duality.
Okay, here we go. Quantum mechanics 101. They can be both a particle and a wave.
Precisely. Neither one fits neatly into just one category. A photon can be a little packet of energy, a particle hitting something, or it can be a spreading electromagnetic wave.
And the electron, too, we usually think of it as a tiny ball.
Right. But experiments clearly show electrons acting like waves. They diffract, they interfere, wave behavior. The sources really stress this duality as like the first big clue.
Okay.
It tells us that even though they seem different, they're both playing by the same quantum rules. Maybe they're not so separate after all.
So they have this shared weirdness. How do they actually, interact? What happens when they meet?
Well, that's where their relationship really gets dynamic. The sources talk about this quantum tango, and the theory describing it is quantum electrodynamics, QED. It's not just like bumping into each other.
Yeah,
It's
right.
more complex exchanges.
What's a key example the sources bring up? The photoelectric effect seems pretty central in the material.
Oh, absolutely. The photoelectric effect is, it's a classic. So a photon comes in, hits a material,
Yeah.
and if it has enough energy, an electron in the material can just absorb that photon's energy entirely.
Then,
And if that energy is more than what's holding the electron in place, what they call the binding energy or work function, then boom, the electron gets ejected, kicked right out.
so the light particle literally knocks the matter particle free. Light liberating matter, as the source puts it.
That's a great way to phrase it.
Yeah.
And this effect, which Einstein explained, was, well, it was revolutionary. It was strong evidence that light does act like a particle, a quantum of energy, transferring its energy in one go to one electron.
Okay, so that's one interaction. Photon gets absorbed, electron gets booted. What about Compton scattering? That's mentioned a lot, too.
Right. Compton scattering is different. The source material uses this analogy of quantum billiards, which I quite like. Imagine a really energetic photon, like an X-ray or a gamma ray, hitting an electron, maybe one that's not held too tightly in an atom.
Like a collision.
Kind of, yeah. But instead of being absorbed, the photon bounces off the electron. It transfers some energy and momentum to the electron.
Making the electron recoil like a billiard ball.
Exactly. And the photon itself scatters off, but now it has less energy, which means it has a longer wavelength.
Okay.
And what that shows, really clearly, is both of them acting like particles, exchanging energy and momentum, just like tiny billiard balls would.
So we've got absorption, we've got scattering, but the sources talk about something even more fundamental, right? This idea that they can actually transform into one another.
Yes. And this is where EFMC4-way really comes alive. It's not just an equation. It describes reality. Energy and matter can literally convert.
So pair production, how does that work? How can light become matter?
It's pretty mind-bending. You need a very high-energy photon. The sources specify it has to be above 1.022 mega electron volts. That's the threshold.
Okay, a super energetic photon. Then what?
If that photon passes close to something massive, usually an atomic nucleus, which helps balance the books for momentum and energy,
Yeah.
the photon can just vanish. And in its place, an electron and its antimatter twin, a positron, appear.
Wow. So pure energy creates a particle of matter and a particle of antimatter.
Exactly that.
Wow.
Energy materializes into mass. It's incredible.
And it goes the other way, too. Annihilation.
Correct. Annihilation is a reverse process. An electron meets a positron,
Uh-oh.
and they annihilate each other. Poof. Their mass is converted entirely back into energy. Usually, it produces two high-energy photons, gamma rays typically, flying off in opposite directions.
To conserve momentum, right.
Precisely. And this isn't just theory. You mentioned applications.
PEAT stands. Positron emission tomography. That uses this, doesn't it?
That's exactly what it's based on.
Yeah.
Detecting those gamma rays from electron-positron annihilation inside the body.
Yeah.
Yeah, direct matter-energy conversion at work.
Okay, this is getting deep. We have these differences, but also this shared duality, these interactions, these transformations. Is there one theory that, pulls all this together?
There is, and that's quantum electrodynamics, or QED. It's arguably the most precisely tested theory in all of physics. It describes all these interactions beautifully.
And how does QED picture these interactions? Not just particles hitting each other, you said.
Right. QED's view is that interactions between charged particles, like electrons, happen because they exchange photons.
Ah, the messenger particle idea again?
Exactly. The source used that analogy, remember? Two ice skaters, they throw a boomerang back and forth.
Right, and the act of throwing and catching pushes them apart or pulls them together.
Yeah. The exchanged particle, the photon in this case, mediates the force. That's the QED picture of electromagnetic interactions.
So the photon is the carrier of the electromagnetic force between electrons.
Mm-hmm. And QED goes even deeper. It suggests that maybe we shouldn't even think of electrons and photons as tiny, distinct objects in the first place.
Oh, how so?
It describes them as excitations, like ripples, or vibrations in underlying quantum fields that permeate all of space-time. There's an electron field, a photon field, and these particles are just sort of localized disturbances in those fields.
So they're fundamentally linked through these fields.
Intrinsically linked, yeah. Their dance is really the interplay of these fundamental fields obeying quantum rules.
Wow. Okay, so let's try to synthesize this. Their relationship is way more than just push and pull. It's symbiotic.
I think that's a good word for it. You start with these apparent opposites, massless versus massive, neutral versus charged, but then you find this shared wave particle, nature. Then you see them interact directly, absorption, scattering.
And then the ultimate connection, transforming into one another, energy becoming matter, matter becoming energy.
Right. And it all points to these incredibly deep principles. Quantum mechanics, the energy-mass connection, and this idea of underlying fields described by QED.
It really challenges your basic idea of what stuff is. The source material wraps this up nicely, saying their dance is a reminder that the universe, fundamentally, is this unified and elegantly interconnected system.
Yeah, it's a profound insight from studying these seemingly simple particles.
So that pretty much brings us to the end of this particular deep dive. We went from looking at how different photons and electrons seem
Their basic stats.
to their shared, kind of weird wave-particle duality, then walked through key interactions like the photoelectric effect and Compton scattering.
The quantum tango.
Then witnessed their pretty dramatic transformations, pair production, and annihilation, linking energy and matter.
And finally touched on QED, the theory that brings it all together, viewing them as field excitations.
It's been quite the journey into light and matter.
Yeah, really fascinating source material to work with. Thanks for providing it.
Absolutely. And it leaves us, and you listening, with something to chew on, I think, based on everything we've discussed from the sources. If photons and electrons can turn into each other, and if QED is right that there may be just excitations in quantum fields, does that change how you think about what matter, or even energy, is? Is it all, at the very bottom, just vibrations? Something to ponder.